Causality and stability of LTI system. So what is causality? An LTI system is a causal if its output y of t only depends on the current and the past input x of t. Assuming the system is initially at rest, that is, its output is y of t equal to 0, then if x of t is equal to delta t, which occur at the moment t equal to 0, the output y of t equal to h of t will be not 0 only when t greater than equal to 0, that is h of t equal to 0 for t less than 0. But as the output and the input of LTI is related by the convolution, so the equation is y of t equal to h of t into x of t, that is minus infinity to infinity h of tau x of t minus tau dt, 0 to infinity h of t x of t minus capital T dt. If the input begins at specific moment x of t is equal to 0 for t less than 0, then we have y of t is equal to h of t into x of t. So in practical term, x of t less than t0, that is y of t less than t0. So, or in other words, no output before input is applied. The input in this case is the delta function which is applied at time t equal to 0. In other words, the impulse response of LTI system has to be 0 for negative time for the system to be constant. Next is stability. So an LTI system is stable if every bounded input produces a bounded output, that is x of t less than bx, then y of t less than by. It is true for all time t. But as the output and input of LTI is related by convolution, y of t is equal to x of t, h of t into x of t. So we solve this equation and we get this y of t. Also we have these two equations for y of t. So LTI system is stable if its impulse response function h of t is absolutely integrable. For LTI system to be bounded, input bounded, for a bounded input, bounded output stable, every bounded signal should produce a bounded output. That is, in system analysis, the linear time variant system is a system which produces an output signal from any input signal subject to the constraint of linearity and time invariance. Inverse head transform. If we want to analyze a system which is already represented in frequency domain as discrete time signal, then we go for inverse Z transform. It can be represented by xn is equal to z raised to minus 1 x of z, where x of n is signal in time domain and x of z is the signal in frequency domain. If we want to represent the above equation in integral form, then xn is equal to 1 by 2 pi j integration of x of z z raised to minus 1 dz. Here integral is over the closed path C, and this path within the ROC, that is region of convergence of x of z, and it does contain the origin. When the analysis is needed in discrete format, we convert the frequency domain signal back into discrete format. Through the inverse Z transformation, we allow the following four ways to determine the inverse Z transform. Long division, partial fraction expansion method, direct computation, and direct inversion. Power series method. In mathematics, power series method is used to speed a power series solution to enter differential equations. In general, such a solution assumes a power series with unknown coefficient. Then substitute that solution into differential equation to find a recurrence relation for the coefficient. The power series method is one of the most powerful analytic methods that physicists have for solving linear differential equations. So these are the equations for power series. Many functions can be written in the form of power series. If we assume that the solution of differential equation is written as a power series, then perhaps we can use a method of undetermined coefficient. That is why we will try to solve the coefficient of the expansion. Next is partial fraction expansion. Partial fraction expansion, also called partial fraction decomposition, and it is performed whenever we want to represent a complicated fraction as a sum of simpler fractions. These occur when working with the Laplace transform, in which we have methods of efficiently processing simpler fractions. Example of this partial fraction expansion, consider this example. Fs is equal to 8 plus 3 by s square plus 7s plus 10s. So we can represent some of the simple fractions by using this. So in algebra, the partial fraction decomposition or partial fraction expansion of rational fraction is an operation that consists of expressing the fraction as the sum of polynomial and one or several fractions with simpler denominator. The importance of this composition lies in the fact that it provides algorithm to various components with rational fractions, including the explicit computation of inverse Z transform, inverse Laplace transform, etc. Next is solution of differential equation using Z transform. In this way, we apply Z transform to the solution certain type of difference equation. We shall see that this is done by turning the difference equation into an ordinary equation. We investigate both first and second order difference equation using Z transform. In particular, the shift theorem discussed at the end of the shift theorem provides a useful method of solving certain type of difference equation. In particular, linear constant coefficient difference equation are amenable to the Z transform technique, although certain other types can also be tackled. So the first order is yn plus 1 equal to yn plus t. So first order again yn plus 1 equal to a yn. So equation will be like this. Other examples of linear difference equations are these two. The key point is that for a difference equation to be classified as a linear, the term of the sequence arises only to the power 1, or more precisely, the highest subscript term is obtained as a linear combination of the lower one. As the Z transforming the convolution representing for a digital filter was so fruitful, let's apply the difference equation. So the difference equations arises naturally in all the situations in which sequential relation exists at various discrete values of independent variables. These equations may be thought of discrete counterparts of the differential equation. Z transform is a very useful tool to solve these equations. The Z transform is useful for the manipulation of discrete data sequence and has acquired a new significance in the formulation and analysis of discrete time system. It is used extensively in the areas of applied mathematics, digital and signal processing, control theory, population science, economics. These discrete models are solved with difference equation in a manner that is analogous to solving continuous model with differential equation. The role played by the Z transform in the solution of difference equation correspond to the played by the Laplace transform in the solution of differential equation. The function notation for the sequence is used in the study and the application of Z of transform. Consider a function x of t denoted by t greater than 0 and it is sampled at different times where t is sampling period. So to solve a linear constant coefficient difference equation, there are three steps. Replace each term in difference equation by its Z transform and insert initial conditions. Solve the resulting algebraic equation. Thus gives the Z transform y of Z of the solution sequence and then find inverse Z transform of y of Z. Thank you.